Hi everyone, my name is François Pacaud, and today I will discuss about automatic differentiation on the GPU. Why do we need automatic differentiation on GPU for our use case? To solve large-scale nonlinear problem. In optimization, this kind of large-scale nonlinear problem are ubiquitous in engineering. And most of them require a fast evaluation of the Jacobian of the constraints in sparse format, and a fast evaluation of the sparse Hessian, W, defined like that. So in this talk, we will extend on existing work in Julia, that is jump.gl, and propose some idea to develop a vectorized modeler entirely in Julia. In my postdoc, we are mostly interested in solving large-scale optimal workflow problem. This problem is ubiquitous in nonlinear programming. So why is my community obsessed with that problem? I mean, this is quite an interesting problem because it is large-scale. We have benchmark easily available, for instance in Pacaud or PGLibOPF. But it's also a very good proxy problem for various problems in engineering. And here we built on the recent initiative Rosetta OPF, which provides a generic benchmark for OPF in Julia. The goal of this package is to benchmark different AD backend and to find which one is the most suitable to solve large-scale OPF. As you recall, here is the shape of the OPF problem. We want to minimize a cost function subject to some constraints, equality constraints, which are often denoted by the pool of flow equation. These equations are super sparse because they connect only nodes between each other through the edges in a graph, and nonlinear. Each flow on an edge depending on voltage angle and voltage magnitude V. What happens if we try to implement the OPF in jump if we use the current existing backend? I mean, if we look at Rosetta OPF code, we get the following transcription. So we get 4 times NL with NL the total number of edges in the graph, nonlinear branch flows. So this is the PYG and QYG we defined before. And these 4 constraints are defined using this NL constraints macro, and we'll build a nonlinear model under the hood. That to define the nonlinear branch flow on each edges. Then we connect the edges together on the bus of the network. To do that, we use the following linear balance equations. These equations are linear, so we use the macro add constraints. So all the nonlinearities in the problem are embedded inside the nonlinear branch flows we define on the edges of the network. So, as we can see, we can build a model in jump and generate a nonlinear model. The problem is jump manipulates only scalar expression. And this is a drawback because that means we cannot parallelize very well the evolution of such a model. So what happens if we look exactly at what's under the hood in jump? If we use a recently developed MW nonlinear backend, jump will output the following 4 times NL expression trees. For each constraint, each nonlinear branch flows in the network, we get an expression trees. So that means we get, for instance, in this network we have 34 expression trees, and we have to evaluate each one of them. So at first, we may think that, okay, we have 34 different expression trees, but it's easy to evaluate that in parallel. We just have to write the following loop and add this macro. And it's exactly what it's implemented in the package symbolic.ad.gl. The problem is threading has some overhead, and in fact, it's usually not direct to parallelize the evaluation of model if we use that way. So we propose in that talk to use a different approach and to evaluate all the constraints in a single block. So instead of parallelizing the problem at the outer level, expression trees by expression trees, we will build a single vectorized expression trees and evaluate the model all in once. That will allow to use SIMD parallelism in our automatic differentiation backend. How to do that? We first look at the math of the problem. And we use this recently introduced nonlinear basis. For more reference, please have a look at this article. And we define the nonlinear basis in the following way. The intuition is we factorize all the nonlinearities in the problem inside the nonlinear basis. And at the end, once we have evaluated the nonlinear basis, we get a large-scale vector with a dimension equal to 2 times the number of branches plus the number of buses in the network. The advantage of the basis is we have to evaluate this expensive cosinus and sinus term only once. Once the basis is evaluated, we can recover all the different constraints, the pure flow constraints or the line flow constraints, or whatever, using only sparse matrix vector operation. And this sparse matrix vector operation will carry over the structure of the network. So for instance, in the vectorized model, the pure flow constraints rewrite the following way. So we have some sparse manipulation of the power generation on, the active power generation and the reactive power generation, minus the loads, plus a sparse matrix applied to the nonlinear basis. And if we can evaluate the basis fast and compute the sparse matrix vector operation as a place, we can get a fast evaluation of the power flow constraints. In Julia, it translates to the following code. So here we use kernel abstraction, a generic package that allows to write down automatically GPU kernel. Kernel abstraction is a portability layer. That means we can generate kernel for CUDA, for AMD, or more recently for OneAPI.jpg. The good news is, once the GPU kernel is generated, we can use SIMD parallelism under the hood to evaluate the nonlinear basis. Then we can recover the pure flow constraints J with one matrix operation. And it proves that this sparse matrix operation, SPLV, is very fast if we use QSparse. Long story short, if we use both QSparse and kernel abstraction, we can evaluate the pure flow equation entirely on the GPU. Now it remains to differentiate the model, because we want to evaluate the Jacobian on the pure flow and the Hessian. The good news is forward diff is already compatible with CUDA GPU. Please have a look at the following article as a reference. So here we use forward diff to evaluate the following Jacobian product. We take the Jacobian of the pure flow that you can observe like that. We use some matrix compression with some optimal coloring algorithm to reduce the total number of Jacobian vector product we need to evaluate the full Jacobian. And then we generate a vector of dual numbers with p different partials vector. So here p equal to 3. On the following block denotes the memory layout of one dual number in Julia. So usually, as the Jacobian is very sparse, we get a very few number of colors in our model. That means we can compress by a lot the total number of Jacobian vector product we need to evaluate the full Jacobian in sparse format. The question is, okay, we have a GPU kernel generated with kernel abstraction, and that's compatible with forward diff. We are covered with that article. But we have also to differentiate the sparse matrix vector operation. Luckily, this operation is linear, so we can use a trick and we can reinterpret the vector of dual numbers as a matrix, real valued, exactly as depicted in that picture, right? this is when we interpret that vector as a block that is as a real valued matrix. Or we evaluate the product SPMV as a SPMM operation. If we are on the GPU, this parallelizes quite well if the matrix is CSL. Unfortunately, generating the reverse parse is a different story, because in Julia we don't have any AD backend mature enough to support the reverse mode we want to evaluate the OPF model. I mean, we have one mature AD backend, jump. The problem is, as we saw before, it's not compatible with the GPU. We have good hope that in the future the package Anzai will solve that issue. But the problem is this package is not ready yet. But hopefully in 1 year we will be able to generate everything automatically. Before that, we are forced to use a manually generated kernel to evaluate the adjoint of the basis. This is fairly easy to do because all the nonlinearities are factorized in a single function, and we just have to do the job and derive all the operation manually. The good news is then it's quite easy to recover the adjoint of the different expression, because in the linear algebra language they translate to the following transpose operation. Suppose now that we have both the forward pass and the reverse pass implemented. That means we can evaluate the second order information, that is a Hessian, if we use a forward over a reverse pass. We use exactly the same procedure as for the Jacobian. And we use optimal coloring to evaluate the full Hessian with one Hessian vector product HV, where the vector V is again a vector of dual number. And to do that, we exploit the same linear algebra trick as the one we described previously. Here is a small benchmark comparing our new AD backend running on the GPU and on the CPU with a reference. And for us, the reference is jump with the default AD backend, the one currently implemented in jump. In the benchmark, we exploit different cases from MatPower with growing sizes. It's important to note the total number of colors we get in the Jacobian. And for some reason, the case big as 9000 get a higher number of colors than the other cases. So what happens if we look at the graph? At first, on the smaller cases, it's not worth to evaluate our model on the GPU, because we are slower than jump. Yes, here everything is scaled by the time spent in jump. So that means if we are on this line, we are exactly as fast as jump. So at the beginning, the GPU backend is not as fast as jump. Jump is faster. And as we increase the size of the problem, the GPU backend is becoming faster and faster, even compared to our own CPU backend. On the larger cases that we use, so case big as 9000 and case active 25K, our AD backend is between 5 times to 10 times faster than jump. Now what happens if we want to solve the full OPF problem using an optimization solver? So here we solve the full OPF problem, including both power flow constraints and line flow constraints, with the custom solver ManNLP, also written in Julia. And we solve all the KKT system with the linear solver HSL LA27. So the only difference between these 3 different implementations are the AD backend, and for jump, use a slightly different model than Argos, because Argos is removing some variable under the hood. So this benchmark is only indicative, but still we can observe that on the larger cases, case active 10K, 25K, and 70K, Argos is about 2 2 times faster than jump with the symbolic AD backend, recently developed by Oscar Dawson. To be honest, it's a bit deceptive, because we're using the GPU, and still we're not as fast as jump. I mean, we are just 2 times as fast as jump. So it's not a great speedup. But Argos is just a prototype, but it's also nowhere near Power Model's robustness, because Power Model is a very well-tested package, whereas Argos is right now still a prototype. So what happened next? I mean, GPU are good for parallelization. So what happened if we extend the optimal power flow problem to the stochastic world, where we have n different uncertainties to tackle? In that case, the stochastic OPF we write in the following way. We want to minimize the sum of the objectives along the different scenarios, subject to some coupling constraints. On one power flow equation on each scenario, Cy. Here we observe that if we can evaluate in parallel the following parameterized functions, G1 to Gn, or if we can exploit their common structure on the GPU to fasten the evolution, we can get a fast evolution of the stochastic OPF on the GPU. In fact, this setting is quite favorable for us, because we want to exploit in the near future the coming exascale architecture, which are GPU-centric. So in that kind of architecture, one node has 6 or 8 GPUs that we want to exploit. So if we come back to the stochastic OPF problem, that means the solver wants to use all the GPU to evaluate the model. So we will compute a number of batch, capital K, for instance, or depend the computation of the K first power flow equation on one GPU, then the K plus 1 to 2K next power flow equation on 1 over GPU, and so on. In that way, the evaluation of the model is fully parallel. We first parallelize the evaluation of the different power flow equation with MPI to use different GPU, and then on each node, on each GPU, we exploit the parallelism of the GPU. So at the end, we get a model with 2 levels of parallelism. That was how we devise our AD backend. In fact, it's more or less equivalent to re-implement struct_jump.gl, but at exascale. It's also important to note that in the following result we will show, we will use a custom solver to solve the resulting KKT system. We won't use MA27, because we want to solve everything in parallel. So that's the figure we get. In the first experiment, we compared Argos, our code, on the GPU with jump. Jump using both the reverse AD, so the classical AD backend, and symbolic AD.gl. So it's interesting because as we increase the size of the problem and the total number of scenarios capital N, it's getting harder and harder to evaluate the model with pure jump. Or at some point, the problem is just too large for jump to be tackled efficiently. And it's not the case if we use symbolic AD. So in our observation, symbolic AD is just surprisingly good to solve OPF problem. But it's able to scale well up to the larger cases, case 9000 PGS with 30 scenarios. Argos is also able to scale, fortunately. And again, the speedup is still limited. We get between 3 to 5 times speedup compared to symbolic AD using GPU, whereas symbolic AD is using sequential code on the CPU. Then we run a second experiment. We took Argos on one GPU and we parallelize the code with MPI on 2 GPU. And in that experiment, we observe that the parallelism is very good. We scale linearly with the number of GPU. So this result is still experimental, so we are using only 2 GPU, but we expect these results to hold with a larger number of GPU, so with 6 or 8 different GPU. But we are planning to run some experiment very soon on theta exascale computer at Argonne. So, if we have a look directly at the larger case 9000 PKS with 30 scenario, we observe we can divide by 2 the total time spent in the AD using our custom parallelized AD backend. So, at the end, if we compare the same code running with jump on symbolic AD, we get approximately a 10 times speed up if we use parallelism on the GPU with MPI. Where all this is leading us? So, as we have observed, it's very hard to build state-of-the-art. Especially for OPF, symbolic AD is just too good for our code to be competitive with. I mean, it makes absolutely no sense to use the GPU if we get only a 2 times speed up compared to a sequential CPU code. Still, we get some interesting speed up if we manage to write down a parallelized code exploiting different GPU. And this context is still very favorable to the upcoming exascale architecture. That's the reason why we believe that the vectorized modeler is one of the features of nonlinear programming, if we want to at least to exploit the emerging SIMD architecture. So here we have a very simple expression tree, right? Because we pass the input variables, the voltage, magnitude, and angle. We evaluate the nonlinear basis, and then we evaluate the power flow constraints. But we can imagine more complex model, right? With different bases to evaluate, and different expressions, both linear and quadratic, remixing inside over the linear kernel. And you can imagine everything you want. You are only limited by your imagination. But we believe that such a vectorized modeler can be implemented inside general score directly to write down the adjunct run explicitly if they are available. And if they are not, we have good hopes that we can use at least unsigned to extract the adjunct automatically. This means at some point we will have to revisit the way we write down the jump abstract symbolic trees in order to support vectorized expression. But we will love seeing some work on abstract expression tree inside MOE nonlinear. And of course, we will be happy to help on that. So I hope you find this talk interesting. And if you have any question, I'm still available to answer them. Thanks a lot for listening.